Okay, thank you very much for having me here. So I'm going to talk about some dark matter phenomenology at higher orders. Already the stage has been set as far as the higher order computations are relevant. But why this dark matter phenomenology? So I'll try to actually motivate that as well. For me, these are actually places where you can play and learn more about these very complicated and mathematical objects. So dark matter, of course, it's one of the most important aspect of new physics that we are interested in. But often we have been talking about dark matter in models like supersymmetry, or we have been looking at EFT models. In recent past, there have been interest in what are called basically simplified dark matter model, which are somewhere in between. They fill that gap where you don't have too much simplicity as well as you don't have too much complications because of the complete dark matter model like MSSM. So typically what you have in such models, you have a dark matter candidate, you have a mediator which connects the dark matter with the visible world or the standard model. So there are many classifications of the simplified dark matter model where you have S channel, T channel, mediator and so on. Among that, there is a classification of mediator which are colored, basically which interact with the quarks or gluons. And in that, there is a very specific model which is unique in itself, and I'm very happy to talk about this here in ISC because the model is basically the thesis of one of the ISC PhD student. So this model where you have a dark matter candidate and you have a mediator which is colored and it interacts with the gluon through gauge interaction. Okay. So you have got basically coupling of phi, which is the mediator with the gluon, and you have a dark matter and mediator coupling, which is denoted by lambda d. Okay. So a lot of actually phenomenology already exists around the standard colored mediators. The literature is full with that, and some phenomenology, which of course, as I mentioned, was done here, and I happen to be part of actually one of those works where I came across this model, and we will see that this model has very much similarity with the Higgs phenomenology. This is where actually my interest is. So this model has basically EFT description, where if the mediator is very heavy, then you come across this operator where dark matter effectively interacts with the gluon. Okay. Okay, so what we know already at the leading order, if I look at the exact theory, then one is interested in computing this annihilation cross section, dark matter annihilating into say colored particles, say for example here gluons, and these are actually loop induced. This is something very unique about this model. Normally you have these tree diagrams for the annihilation and monojet production and all those things, but this is what the unique about this process is. And this loop suppression actually helps in like making this chi as a dark matter candidate, which is like a WIMP, right? You want a weakly interacting massive particle. So weakness is induced by these loops. That's what the peculiarity or the speciality of this model is. So these are actually simple loop, although they are loop, but they are actually finite. You can compute in the non-relativistic limit this cross section, and you can. This is the result which I have taken from the work which already exists. You can study that what happens in various kinematic scenarios. For example, if mass of phi is less than chi, then what kind of relic density constraints you can put on the model parameter, in this case basically m phi versus m chi. You can also study the EFT versus the exact theory, as for example here I am showing you this cross section versus the EFT cross section, and that suggests that you should be basically looking at simplified model more seriously than EFT alone. Okay, then the second observable of interest is these monojet studies, which one is interested at, for example, at the LHCs, where you have missing energy which is due to the production of the dark matter, and then you have jets. Again, you can see how EFT and the exact description they compare with each other. And then this is the work where I was also involved, and we computed this kind of diagrams, which again, although one loop happened to be finite, ultraviolet finite, so computations are not that difficult. However, and then we actually made some studies that what is the significance for various parameter values. For example, phi, that the color mediator you have, you want to know basically in which color representation does it live, so that becomes a parameter. Then what is the strength of the dark matter coupling with the phi, those are all actually parameters. And then what is the value of phi, and so on. Anyway, while studying all these things, what you notice, two things. One is basically there are colored interactions which are involved, like phi interacts with gluon through this strong coupling. Okay, and these are actually loop induced processes, so they are definitely suppressed. However, this process is very much like actually producing, say for example, Higgs plus jet. And these loop induced processes where gluon is in the initial state, they suffer from very large scale uncertainties. In certain cases, the scale uncertainty can be up to 50%. Okay, so that's one of the reasons why you may not be very happy with just with the leading order phenomenology, although you are talking about new physics, but still there is actually some value in looking at these phenomenology at higher order itself. Okay, so considering higher order, in this case the QCD corrections, what we are talking about, pretty much a standard higher order correction where you want to know what are the real contribution, what are the virtual contributions. Already in the previous talk you heard a lot about the virtual contributions, but in this case what I want to focus, because I have to still really go a long way, I am only in the beginning of this study, so but as far as this talk is concerned, I am going to limit myself to what are actually virtual corrections which are relevant to the higher order corrections, whether it's annihilation cross section or the monojet production. So what it means, I am talking about these kind of diagrams, two loop diagrams, because leading order is already one loop, so virtual contributions, they are going to appear at two loop. So in this case it's a 2 to 2 process, in this case it's actually a 2 to 3 process, but because of this contact interaction, topologically it is actually a 3-point function at 2 loop, and this is a 4-point function at 2 loop. So there is a simplicity in complexity because of this contact interaction. So what we are going to do about, if I have to, so I want to basically focus on the form factor computations, and here is the amplitude for these two cases. There are actually other contributions as well, which I will mention as I proceed with my talk. So computing this amplitude is effectively, you want to basically have computation of these form factors, because you know what the Lorentz structures are there. For example, in this case, where you are interested in dark matter annihilation into a pair of gluons, there is only one form factor. In the case of monojet signature, the amplitude is a bit more complicated because of more particles involved, and you come across basically 4 form factors. This is very generic to all orders. So what you are saying that having this amplitude at higher order is to have form factor at higher order. So F has expansion in alpha S. And there is a standard technique, a projected technique, those who do loop. I don't have actually more, I don't have time to get into that, but of course we can talk offline about it. So this projected technique you use to connect these form factors with the Feynman diagrams, and therefore the integrals about which you already have heard a lot. Okay, so without getting into the details of calculation, which I think Ravi has already explained all the steps, those steps are common here. I will just mention some of the results that we have and some of the features. So for example, if I look at the two loop form factors for the annihilation cross section, chi going to blue, what I notice that there is actually two mass parameters. One is S, the energy, and the m phi, and through which I will have basically one dimensionless parameter. So my integrals, which in this case basically can be classified in these 3 topologies, which I am calling basically planar and non-planar topologies. So the whole idea is that all the diagrams, they can be converted, they are basically expression of integrals, and those integrals can be put in one of these actually topologies. And what among these topologies, what you find that if you simplify, you come across total 18 master integrals. That's what basically you have. And master integrals, Ravi has already mentioned that how to solve them. This is very much similar to, as I mentioned, Higgs production at the LHC. So we have a way, basically the only difference is that in the case of Higgs you have a top quark which goes in the loop, which is a fermion. In this case there is a colored scalar which is going in the loop. So there is slight difference, but lot of help you get from results which are already available for the Higgs production. And here I have basically the result which I have obtained after doing the ultraviolet renormalization and removing the infrared singularities, because these diagrams, they suffer from singularities which you regularize in, say for example, dimensional regularization and so on. So that's all actually at say 2 loop level. It's a very compact expression. There is only single variable, or you can say 2 scales were involved, and they are written in terms of special functions which are nothing but the iterated integrals called harmonic polylogs with the weight up to 4. It means how many actually iterations of integrals are involved. Okay. Now at 2 loop level, when you want to basically have this prediction for the cross section, you know these virtual contributions, they interfere with the leading order diagram. What we have computed, the 2 loop form factors, they have singularity, infrared singularities, which are of the order of 1 over epsilon square, which requires you to compute this 1 loop also up to order epsilon square in factor, because at the end of the day, this is the quantity which is going to contribute to your phenomenological result for the cross section. So we compute that as well. We have this is a very trivial expression, it is just a log, and you have order epsilon and order epsilon square. So that basically tells you that as far as the virtual computations are concerned, that's actually we have all the results. Now going at 2 loop level, there is actually a new channel which is not present at the leading order, because there is no direct interaction between phi and the quark, what I have considered. At 2 loop level, you also come across chi-chi decaying into 2 quarks, and this channel is appearing for the first time. So as it happens, although it's a loop, I said 2 loop, but since it is appearing for the first time, it is supposed to be actually finite completely, both infrared as well as UV. And this is one of the strongest check in your calculation when you are going through it, because as you will see, there are several diagrams will be involved. In this case, for example, we come across 20 master integrals, which is 2 higher than the previous case. Although the the topology, only one topology is sufficient to express all the integrals, but the complication comes here because I have got M phi, which was already there, and I have got MQ. Because these processes, because of the helicity conservation, they are 0 if quark mass is 0. So this is relevant for dark matter decay into massive quarks. So that's the reason why I have actually another scale, and the moment I have actually more scales in my problem, this becomes very difficult. So here is the result, which is completely finite. We have tested it because we have all the expressions. In this case, the expression is actually really long. If I wanted to write it, I will have actually 3 more pages, but still they are, I think, much simpler than what Ravi would have. Okay, so these are just actually form factors in terms of these dimensionless parameters. In this case, I have introduced W and Z. I'm really far from making any physical prediction with that, but just to see what are the features of these form factors, we have tested something which makes sense in the sense, for example, W, which is related to M phi. I want to know for different values of M phi how my form factor behaves for the variation of S, and similarly Z, which is a function of which is basically equivalent to choosing value of quark mass, is basically here. Okay, anyway, like yeah, in this case basically you get not harmonic polylogs, but what is called basically generalized polylogs, and these are 328 of them. Okay, so coming back to the monojet now, in this case, as I already mentioned, things are much more complicated. So I still have 3 topologies, but there are actually 4 scales in my theory, which actually makes this problem very intractable, because I come across 120 master integrals. Some of them are simply not available. What it means, you need to compute them, and solving master integrals with multiple scales is not actually an easy task. So we are actually still trying to manage this, but what I want to actually mention, which happens to be actually my last slide, once you have these form factors. As I mentioned, you are going to basically start talking about the phenomenological results. Okay. What does it mean if you want to have phenomenological result? It means basically you have to do the computation of real corrections as well, meaning computing these kind of diagrams. Now, if I were doing basically, say, analog correction to a leading order process, what I need to basically be doing, I need to compute the real corrections in dimensional regularization, this integration, so that I can regularize my singularities and ensure that the cancellation of soft singularities between the virtual and real happens to have a finite result. Because of the presence of the loop, this is not a trivial task to have basically this kind of real corrections. Okay, so these are real corrections which are at one loop level. Okay, so this poses actually challenges of both the loop as well as phase space integration in n dimensions. Okay, so there is actually a long way to go before I can have actually phenomenological result. However, once we hope to have form factors for the monojet very soon, and for the annihilation cross section we already have everything, and the result is actually not difficult to compute. So apart from having phenomenological result, this calculation would also allow us to test something which we already did at the leading order. For example, checking the validity of EFT. So the same question is basically applicable at higher orders as well, that what kind of how to validate the EFT at higher orders. So having these results will not only have some phenomenology for the dark matter both at the colliders as well as indirect searches, but also it will allow me to formally understand the EFT approach, the complementarity between EFT approach and simplified model approach. So here I stop. Thank you. Yeah.
Thanks a lot, Ambresh. One question.
So what is the question, whether they are actually relevant or not? Right. So see, as I told you, yes, if you look at the new physics things, there are certain situations where you can show that if you don't have these higher order corrections, because these higher order correction basically they give you a correction of more than 100%. Okay. And one of the reasons for that is that at leading order, when you have only one channel, but at hadron colliders, when you go to higher orders, new channels also open. So that's one of the reasons why you still want to look at certain processes at higher orders, though they are related to, say, for example, new physics. And the other reason, basically, as I told you, is that it's actually it's a toy model also for you, where a lot of things which are being done, these are actually not process specific. Once you have them, they can be basically applied to something which is more relevant, which can pop up actually, say, some after 30 years. For example, when we talked about DIS, the first time the calculation was done almost 40-50 years ago, and it has again caught up the attention, and they have been actually able to do it because they had actually everything.
Okay, Ravi, quickly.
So in both the monojet case and the there are UV divergence. No, this is not actually. So this is UV complete. It's simplified, but UV complete. Yeah. Renormalizable. Yes. Yeah. It becomes. No. So for example, gauge invariance has been ensured. So in having the interaction of phi with the gluon, the gauge invariance have been ensured. Yeah.
Okay, with this we conclude this talk by thanking Ambresh Shivaji once more for this very nice program.